Hi students, this is Sivakumar, 11th standard mathematics. Now chapter number 1. Exercise 1.2. Before doing that exercise 1.2, you must be knowing some definition. First I start with the constants and variables. A quantity that remains unaltered throughout a mathematical process is called a constant. A quantity that varies in a mathematical process is called a variable. A variable is an independent variable when it takes any arbitrary value not depending on any other variables, whereas if its value depends on other variables, then it is called a dependent variable. I'll explain by giving example. You can understand easily. Listen. First one, area of a triangle that is represented by the letter capital A. You know the formula for area of a triangle: length into breadth. Here, length and breadth are independent variables. But the area, to find the area, that depends on L and B. Area depends on L and B. Therefore, that capital A is a dependent variable. Like that. Area of a circle is represented by the letter capital A over here. You know the formula pi r square. Pi is a constant. Capital A is a variable or is also a variable. Here or is an independent variable. It doesn't depend on anything. Therefore, it is an independent variable. But capital A depends on the value of R. So it has to depend that R value. Therefore, capital A is a dependent variable. And the third one, volume of the cuboid, you know the formula, length into breadth into height. Here, small l, b, h and all variables, even b variable only. But L, B, H and all independent variables. Each and every one is not depending others. Therefore, they are called independent variables. But to find the volume of the cuboid, that V depends on the values of L, B and H. Therefore, V is a dependent variable. So, capital A and capital V are dependent variables. L, B or H and all independent variables, and pi is a constant. Okay, now definition 1.1. Listen, a subset I of R is said to be, here R refers a real line. I have drawn a line here, a real line, said to be an interval if capital I contains at least two elements. Here I consider 1 as A, 5 as B. I consider 1 to 5, that is capital I. I contains at least two elements. What are the two elements? Here A and B. So at least means minimum of two elements. And A comma B belong to I, and A is less than C and C is less than B. Now look at the diagram here. I have taken three numbers, 1, 3 and 5. 1 I consider as A, 5 I consider as B and 3 I consider as C. 1 is less than 3, 3 is less than 5. At the same time, 3 belongs to the interval of 1, 5. So A is less than C, C is less than B, C belongs to the interval of I. Okay. Geometrically, what is given? Intervals corresponds to rays. Here, 1, that 1, small a to the right hand side extension. Here, small a to the right hand side extension, that is called a ray. And 5, that is B. 5 to the left hand side extension, that is also a ray. Then 1 to 5, that is a line segment. This one is a line. Okay. From A to the right hand side extension is a ray. 5 to that left hand side extension also array. This portion, that 1 to 5 or A to B in general, that is a line segment. From here to here, that is a line. Particularly this line is your real line. In real line, we have uncountable numbers are there. Given between 1 and 3, uncountable numbers are there. Even we can say 1.1, 1.2, 1.3, 1.8, 2.1. So uncountable numbers. Okay. Now, types of intervals. There are many types of intervals. Let A, B belong to that set of all real numbers. Capital R represents set of all real numbers such that A is less than B. The following table describes various types of intervals. It is not possible to draw a line if a point is removed. So we use an unfilled circle. This is unfilled circle to indicate that point is removed, and use a filled circle. This is a filled circle, and it indicates that the point is included. Look at the table. First one, A, B. Look at the notation. A, B. Look at the bracket. Normal bracket. Left open. What it is called? Left open, right open. In set form, you can say set of all x such that A less than x less than B. All the values of x between A and B. Between A and B. So diagrammatic representation. Look at the diagram. This circle represents unfilled circle. Unfilled circle means that particular value is excluded, excluding A and B. Now look at the second one. Left closed, right closed. What it is called? Left closed, right closed. Look at that. Less than or equal to. Here also less than or equal to. Since we have left closed, right closed, look at the diagram. This one is a filled circle. It is also a filled circle because the circle is highlighted. So what it is called? Filled circle. That means inclusive of A and B. That means including A and B. Next one, third one. Left open but right closed. Left open, that is less than. Right closed means less than or equal to. That means excluding A, including B. So that here that is unfilled circle, but this one is a filled circle. Now the last one, fourth one, left closed, right open. Since left closed we have mentioned less than or equal to, right open, this is right open bracket, that is strictly less than B. So what it means? Including A, filled circle, excluding B, so unfilled circle. These are all finite interval, countable number of elements. But look at that, left open A, right also open, but what is here? Infinity. It is a ray, one end point and another one, it never ends, it is going on, it is a ray. A less than x less than infinity, excluding A. Therefore what circle it is? Unfilled circle. Next one, including A and infinity. So including A means A less than or equal to x. Since less than or equal to comes now, you have to put the filled circle. It is going on from here to that right hand side is fully extended. Uncountable numbers are there, therefore it is an infinite set. Next one, minus infinity to B. Minus infinity to B means B here, minus infinity in the left hand side, minus infinity to B. Always you have to consider the interval from left to right only. Don't say B to minus infinity. You have to say minus infinity to B. Since it is strictly less than B, this one is the unfilled circle. Next one, minus infinity comma B. B, that is closed one. Since it is closed bracket, less than or equal to that. Since we have less than or equal to, here we have that filled circle. That means minus infinity to B. And last one, minus infinity comma infinity. both the ends being extended. It is a set of all real numbers, no end at all, even in the left hand side and the right hand side. So what it refers? It is set of all real numbers. Minus infinity, comma infinity can be represented by capital R. Okay. Now the definition of a relation. Listen. Let A and B be two non-empty sets. You know the meaning of non-empty sets? A set which has at least one element, that is called a non-empty set. Here A and B are two non-empty sets. A relation capital R from A to B is defined as a subset of the Cartesian product of A and B. Already I have learned about that A cross B in the previous exercise. So how to represent that relation? Symbolically, R is a subset or equal to A cross B. Subset or equal to A cross B. While working out the problem, you can understand the concept of the relation. Okay. Now, it's a very important part in this exercise. Let S be a non-empty set. Let R be a relation on the set S. Then, the relation R is said to be a reflexive if A is related to A for all A belongs to the set S. R is said to be symmetric if A is related to B implies that B is related to A. Third one, R is said to be transitive if A is related to B and B is related to C implies that A is related to C. So these three relations are called basic relations. You can understand the concept of a reflexive, symmetric and transitive after giving an example only. First you read all the definition. Next, let us rewrite the definition of these basic relations in a different format. Let S be any non-empty set and R be a relation on S, then R is the same definition in different format. A reflexive if A comma A belong to that set R. Here R refers a relation. For all A belongs to the set S. Symmetric, A comma B belongs to R, then B comma A also belonging to that set R. R is a relation. And the third one, transitive, if A comma B comma C belong to capital R, then A comma C. Look at that, here ends with B, here starts with the C, B. Continuity is there. Then you can write A comma C. A comma C is belonging to that R. R refers relation. The next one, let S be any set, a relation on S set to be an equivalence relation if it is reflexive, symmetric and transitive. If all these three are satisfied, we can say that S is an equivalence relation. We can see some examples. After that, you can understand the concept of reflexive, symmetric and transitive. Illustration 1.4. You are given capital X. X has 4 elements, 1, 2, 3 and 4. And the relation R that is equal to 1, 1, 2, 1, 2, 2, 3, 3, 1, 3, 4, 4, 1, 2 and 3, 1. We have to see one by one. First one reflexive, then symmetric, finally transitive. Right? I have written here. Since you are given only one set X, I have written X for 2 times because we have to find out A cross B. Instead of A cross B, we have X only. No, this is A, this is B. So instead of A cross B, what I have to say? X cross X. You know how to find the cross product. Very simple. Start with 1, 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4. Like that, 2 1, 2 2, 2 3, 2 4, 3 1, 3 2, 3 3, 3 4, 4 1, 4 2, 4 3, 4 4. Have written everything. Now the given relation, here it is. Start with reflexive. In that definition of reflexive, what is given? If a comma a belong to that relation, or for all a belongs to the set S. Here in this example, the set is given as capital X. So a comma a, remember a comma a. Since we have the set X 1 2 3 4, the relation OR must have 1 comma 1, 2 comma 2, 3 comma 3 and 4 comma 4. Then only we can say OR is reflexive according to the definition. The definition, what is given? A comma a. A belongs to the set yes. Here a belongs to the set capital X. Since I have taken 1, 1 comma 1, yeah, 1 comma 1 is there in that relation. Now I am taking 2, 2 comma 2, yes, 2 comma 2 is there in that relation. Now I am taking 3, 3 comma 3, yes, 3 comma 3 also there. Now I am taking that 4. Since we have 4, 4 comma 4 must be there in the relation. No 4 comma 4, yeah, even 4 comma 4, sorry, 4 comma 4. So we have 1 comma 1, 2 comma 2, 3 comma 3 and even 4 comma 4. The first condition is satisfied. So definition of reflexive is satisfied. Therefore we can say OR is reflexive. What is given? It is reflexive. Now we can go for that symmetric. Symmetric, what is given in that definition for symmetric? Look at that. If a comma b belongs to that relation, or b comma a also belongs to the set OR, then only we can say OR is symmetric. A comma b, b comma a. We can check. 1 comma 1, I take 1 comma 1 first. 1 comma 1, the reverse also 1 comma 1. Here it is. Then 2 comma 1 reverse 1 comma 2. 1 comma 2, here it is. Now I take 2 comma 2. 2 comma 2 reverse, again 2 comma 2. Next 3 comma 3 reverse, 3 comma 3 only, it is here. 1 comma 3, 1 comma 3 reverse, 3 comma 1, 3 comma 1, here it is. Now I take 4 comma 4, 4 comma 4 reverse, that is 4 comma 4 only, here it is. Now I take 1 comma 2, 1 comma 2 reverse, that is 2 comma 1, here it is. Finally 3 comma 1 reverse, 1 comma 3, here it is. So in a comma, for every a comma b, we have b comma a in the set OR. Therefore OR is symmetric. So for two conditions are satisfied. One is reflexive, next one is symmetric. Now we have to verify whether it is transitive or not. So what is given in the definition of a transitive? Look at that. What is given? For every a comma b, b comma c belong to OR, a comma b, b comma c belong to OR, a comma c must belong to that OR. Then only we can say OR is transitive. We can verify now in that example. Here I take 2 comma 1 and 1 comma 3. 2 comma 1, 1 comma 3, yeah, that continuity is there. Here ends with 1, here starts with 1, continuity is there. But what is here? Here starting 1 is 2, ending 1 is 3, 2 comma 3, 2 comma 3 must be in the set OR. No 2 comma 3 at all. No 2 comma 3 in OR. Therefore OR is not transitive. Even when such condition is not satisfied, we can say that is not transitive. You can ask, sir, why don't you take 1 comma 2 and 2 comma 1? if I take 1 comma 2 and 2 comma 1, I write over here 1 comma 2 and 2 comma 1. Here continuity is there, correct? Continuity is there. Here ends with 2, here starts with 2. Now 1 comma 1 is in the set. Even though here it is satisfied for 1 comma 2 and 2 comma 1, but the same condition is not satisfied by considering 2 comma 1 and 1 comma 3. If this condition is not satisfied for one such case, we can say that is not transitive. Since 2 comma 1, 1 comma 3 in that OR, but 2 comma 3 is not in that OR. Therefore OR is not transitive. So we can say OR is not an equivalence relation. If all the three satisfied only, we can say equivalence relation according to the definition. Here only two satisfied, reflexive and symmetric only, but not transitive. So we can say OR is not an equivalence relation. Now I can go for the second example. Let capital P denote the set of all straight lines in a plane. Let R be the relation defined on P as L is related to M. What's the condition given? If L is parallel to M. L is parallel to M. We can verify one by one. First I take a reflexive. I draw one line first. That is L. For proving that reflexive, only one line is enough. Now, this particular line is, listen carefully, this particular line is parallel to that same line. Correct? L is parallel to L. What's the condition given? Parallel. For reflexive, you have to consider only one element. Here the element is a line. So, L is parallel to L. Therefore, it is reflexive. Next, I go for symmetric. For symmetric, we need two lines. I take two lines, L and M. According to the definition of symmetric, here L is parallel to M. Similarly, M is parallel to L. So what is given in that symmetric definition? If A comma B belongs to R, B comma A must be in that R only. Like that, L is parallel to M. Obviously, M is parallel to L. So both the conditions are satisfied. Therefore, that R is symmetric. So for two of them satisfied. One is reflexive as well as symmetric. Now I am going to verify whether it is transitive. I take L, M and N. First I take L and M. I draw a line first. Please. L is parallel to M and M is parallel to N. Therefore, L is parallel to N only, no? These two are parallel. These two are parallel. Obviously, these two are parallel. According to the definition of transitive, A is related to B, B is related to C. Then if A is related to C, then only we can say that is transitive. Here the condition is satisfied. Therefore, it is an equivalence relation. All the three conditions are satisfied: reflexive, symmetric and transitive. Therefore, OR is an equivalence relation. Now I go for the third illustration. Let A be the set consisting of children and elders of a family. Let OR be the relation defined by A is related to B if A is a sister of B. Look at that, A is a sister of B. This relation is to be looked into carefully. A woman is not a sister of herself. So it is not reflexive, it is not symmetric also. Clearly it is not transitive, so it is not an equivalence relation. Suppose if we consider the same relation on a set consisting only of females, then it becomes symmetric. Even in this case it is not transitive. I give an example, listen carefully. Here you are given children and elders of a family given. Children and elders of a family, the relation is sister of B. Okay, listen. I take that set capital A as father, mother, son, daughter. 4 members of a family. According to that relation, I consider daughter comma son. I have taken daughter comma son. Daughter is a sister of son for the mother and father, correct? Daughter is a sister of son. According to that a definition of a reflexive, A comma A belongs to R for all A belongs to A. In that set A, I take the daughter only. Daughter comma daughter. That means daughter is a sister of daughter. You are given this is sister. A is a sister of B, that is given. Remember. So daughter is a sister of daughter. Meaningless. Therefore it is not reflexive. Next one. A related to B, then B related to A. Then only we can say symmetry. Look at that. I take this one. Daughter is a sister of son. But son is not a sister of daughter. Absolutely wrong. From here to here, okay. Daughter is a sister of son. But B comma A, that means son is not a sister of daughter. Here belongs, this one doesn't belong. Therefore not symmetric. Understand? Next one, we have to verify transitive. For transitive, A comma B and B comma C belong to R, then A comma C belongs to R. Here there is no pair A comma B in R, no pairs A comma B and B comma C in R. We have only daughter and son, no son and daughter. Therefore it is not transitive. So we can't find two such pairs to find this pair in the relation or. Therefore it is not transitive also. So not reflexive, not symmetric and not transitive. Therefore or is not an equivalence relation. Now I can go for that next example. On the set of natural numbers, let R be the relation defined by x is related to y if x plus 2y that is equal to 21. It is better to write the relation explicitly. The relation R is the set 1, 10. How it comes? Here, set of all natural numbers given. Natural number starting number is 1. I am replacing x by 1 first. Right? If we replace x by 1, what is the value of y? We can find. Suppose I replace x by 1. 1 comes right hand side minus 1. 21 minus 1 is 20. 2y that is equal to 20 means y that is equal to 20 by 2. 20 by 2 that is equal to 10. 1, 10. Like that. I replace x by 2. If we replace x by 2, 2 comes right hand side minus 2. 21 minus 2 that is 19. 2y that is equal to 19 means y that is equal to 19 by 2. 19 by 2 is not a natural number, so that you are not supposed to take x as 2. So that the next value of x is 3. Natural number, next number 3. Replace x by 3 here. 3 comes right hand side, minus 3, 21 minus 3 that is equal to 18. 2y that is equal to 18 means y that is equal to 18 by 2. 18 by 2 that is equal to 9. Okay, 3 comma 9. Like that can give the values of x as 1, 3, 5, 7, 9, 11, 13, 15, 17 and 19. So maximum you can give only 19. So here I take x that is equal to 19. 19 comes right hand side, minus 19, 21 minus 19 that is equal to 2, 2y that is equal to 2 means y that is equal to 2 by 2, 2 by 2 that is equal to 1. So why don't you give x as 21? If you replace x by 21, 21 comes right hand side, minus 21, 21 minus 21 that is equal to 0. 2y that is equal to 0 means y that is equal to 0 by 2 that is 0. You will be getting y as 0. 0 is not a natural number. Therefore, can give the values of x from 1 to 19 only odd numbers. So 1, 3, 5, 7, 9, 11, 13, 15, 17 and 19. Right? So this is a relation. We have set of ordered pairs. Now we can verify one by one. Since we have the starting number 1, we have 1 in x. 1 comma 1 must be there in the relation. Then only we can say that is a reflexive. No 1 comma 1 in that relation. Then as 1 comma 10 belongs to R, 1 comma 10 belongs to R, we have 1 comma 10. There is no 10 comma 1. Reverse one is 10 comma 1. 1 comma 10 is in R, but 10 comma 1 doesn't belong to R. Therefore, it is not symmetric. Next one, we can go for the transitive. We have 3 comma 9 and 9 comma 6. 3 comma 9 and 9 comma 6. 3 comma 9 belongs to R, 9 comma 6 belongs to R, but 3 comma 6 doesn't belong to R. Therefore, the relation is not transitive. Once again, 3 comma 9 and 9 comma 6. We have taken these two. No, here ends with 9, here starts with 9. Continuity is there. 3 comma 6 must be there in the relation, but there is no 3 comma 6. Therefore, it is not transitive. So, not reflexive, not symmetric and not transitive. It is an example for not an equivalence relation. Okay. Next illustration number 5. The set X has 4 elements 1, 2, 3 and 4, and the relation R is an empty set. First we can go for reflexive. Since we have 1 in that set X, 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4 must be in that relation R. So not even 1 comma 1 in that set R, because it is an empty set. Therefore, it is not reflexive. Next, you know the definition of symmetric. If x comma y belongs to R, y comma x must also in the set R. Here no x comma y in R, no x comma y cannot find a pair x comma y in R such that y comma x doesn't belong to R. In that case also we can say symmetric. What is given here? The relation is not symmetric. Not symmetric means it is a symmetric only, because no such pair in that relation. Therefore, it is symmetric. Similarly, we can say it is transitive. For transitive, here is the explanation given in that. Look at that. We can't find two pairs A comma B and B comma C in OR, A comma B and B comma C in OR such that A comma C doesn't belong to OR. Thus, the statement OR is not transitive is not true. Not transitive is not true means it is transitive. Okay. Now, number 6, the universal relation is always an equivalence relation. The next one, an empty relation can be considered as symmetric and transitive according to that statement number 5. Symmetric as well as transitive. 8th one, if a relation contains a single element, then the relation is transitive. I give an example. Suppose I consider a capital A that is equal to A comma B, or that is equal to, or refers relation. It's a singleton set because it has only one element. I have to say the relation is transitive. According to the definition of a transitive, look at that, it's clearly given. We can't find two pairs A comma B and B comma C in OR. We have only one element in that set OR, correct? We can't find two pairs A comma B and B comma C in OR such that A comma C doesn't belong to OR. Therefore, the statement OR is not transitive is not true. See, suppose we have A comma B and B comma C both in OR. Suppose, but A comma C doesn't belong to OR, then we can say that is not transitive. Again I tell you, suppose I take OR that is equal to A comma B, B comma C, not related to that 8th problem. 8th problem we have only one element. Simply I have taken two elements here. We have A comma B, we have B comma C, but we don't have A comma C. Then in that case you can say OR is not transitive. But what is given here? We can't find two pairs. That example number 8. We can't find two pairs A comma B and B comma C in OR such that A comma C doesn't belong to OR. In that case also we can say OR is transitive. So revise all the definitions, example, keep on revising, then only can understand the concept. I will be teaching that exercise 1.2 in the next video. Thank you children. Bye bye.